If you are a biologist or a math student and it's your first time dealing with fluorescence microscopy, there are graphs, diagrams, dyes, fancy technical things, and it all feels confusing. That's totally normal. Your specialty is biology and medicine, not physics. Today I'll explain everything about fluorescence microscopy step by step. And if you're new here, then hi, my name is Eric and I've been working as a microscopy application specialist for over 15 years. On this channel we cover proper theory and real hands-on practice, and we also look at all kinds of things under the light and scanning electron microscope. So let's jump straight into it. Let's start with the fundamentals, the physics. It may seem a bit dry, but it's essential to understand what actually happens in a fluorescent sample. When we illuminate a specimen with light of a certain color, say blue, part of that light passes through and part reflects back. But a tiny portion interacts with the sample in a special way. This is fluorescence. When a molecule called a fluorophore absorbs a photon of high energy, usually ultraviolet or blue light, one of its electrons is excited from the ground state to a higher excited singlet state. The excited electron quickly loses some energy through vibrational relaxation. This brings it to the lowest vibrational level of the excited state. The electron then returns to the ground state, releasing the remaining energy as a photon of light. This is fluorescence. The emitted photon has lower energy, longer wavelength than the absorbed one, because some energy was lost as heat. This difference between excitation and emission wavelengths is called the Stokes shift. So when you excite your sample with blue light, you often see green emission. If you excite with ultraviolet, you might see fluorescence in the whole spectrum, depending on the dye used. Why do we use fluorescence at all? Because using this method we can see things invisible in bright field or phase contrast microscopy. Fluorescent markers, proteins or dyes bind to specific structures. For example, DAPI stains cell nuclei. Other dyes stain mitochondria, cytoskeletons or even viruses. This gives us contrast and a lot of structure information. Fluorescence is used with viruses for research purposes, where the virus particles or viral components are tagged with fluorescent markers. You can visualize viruses like rabies or tuberculosis even though they are smaller than the optical resolution limit of your microscope, because in most cases you see their fluorescent glow rather than their actual structure. Now let's talk about light and filters, the most exciting and important part. Visible light ranges from about 350 nanometers violet to 720 nanometers deep red. Fluorescence microscopy works in and around this range, including ultraviolet and infrared regions. Filters control which wavelengths pass through the system. This red filter only passes red light. A blue filter can be short band, called SB, letting only blue through, or long pass, letting blue and everything longer, green, yellow, red, through. Filters are labeled like 470/50, meaning a central wavelength of 470 nanometers with a 50 nanometer bandwidth. 470 LP means a long pass filter that transmits everything above 470 nanometers. Some filters, called multi-band filters, transmit several narrow ranges, for example 380, 470 and 540 nanometers. They are complex and expensive, but useful for multi-channel imaging with LED light source. A dichroic mirror is a special component that reflects short wavelengths and transmits longer ones. For example, a mirror rated at 500 nanometers reflects blue light but lets green and red pass through. This is how we separate excitation and emission light path in the microscope. Modern fluorescent microscopes use three main types of light sources: mercury lamps, metal halide lamps, and LEDs. Mercury and metal halide lamps emit white light across the whole spectrum, so we use filters to isolate the excitation band. LEDs, on the other hand, emit a narrow wavelength range, making them much simpler to use. No excitation filter needed in many cases. They are efficient, long-lasting, and now dominate modern systems. For sure, we can also use lasers, but confocal microscopy is the long story. Someday we'll cover it as well. In a fluorescence microscope, light passes through an excitation filter, hits the dichroic mirror, and reflects down onto the sample. The emitted fluorescence travels back up through the mirror and passes through an emission filter, which allows only the desired wavelengths to reach the camera or eyepieces. These three components are housed together in a filter cube or mirror cube. Some microscopes have manual sliders, others use automated turrets with multiple cubes for different dyes or channels. Let's move a little closer to the hardware. In front of us is a standard transmitted light microscope, and we're about to install a third-party fluorescence illuminator on it. The objectives on this microscope are designed for infinity correction. That means that after the objective, the light travels as a parallel beam. And that's great for us, because it allows you to place all kinds of components directly into the optical path, without any changes to simple bright field image and overall microscope performance. Quick announcement: I don't have any commercial sponsors. I run this channel completely on my own, so your subscription is the best way to support me. Thank you. Okay, let's continue. We remove the tube, attach the fluorescent illuminator, and put the binocular back in place. And yes, of course, fluorescence imaging normally requires fluorescence optimized objectives. They are designed for two-way transmission, they handle UV light efficiently and generally provide high resolution. I will make a dedicated video about microscope objectives, but for today's demonstration we will skip this topic. Multi-channel fluorescence allows us to capture images from several dyes simultaneously. Because fluorescence signals are usually weak, we often use high-sensitivity monochrome cameras with cooling and low noise. Each image corresponds to a different dye channel, usually blue, green or red. After acquisition, we assign colors in software like Photoshop or special microscopy software, overlay them and get those famous multi-channel composite images. Advanced multi-channel LED systems combine several LEDs and dichroic mirrors into one optical path. You can switch channels electronically without changing filters, making acquisition fast and flexible. Let me walk you through an example of how to choose the right filters for your experiment. Let's say you're working with a microscope that has a color camera and you need to capture a two-channel image using DAPI and FITS. If you're using a white light source like a mercury lamp, there are a couple of options for filter cubes. The first option is a single multiband cube. You just choose the filters according to your dyes. The excitation and emission ranges should match as closely as possible. A multiband cube is convenient because you can see both fluorescent channels at the same time through the eyepieces and on the camera, but when it comes to separating the channels later, things get complicated. For example, if your FITS signal is much brighter than your DAPI signal, you simply won't be able to balance the fluorescence properly, and your final image will end up with uneven signal levels. The second option is two separate filter cubes. In this case, you'll need two cubes that match your dyes. With this setup you can get two images, one in the blue channel and one in the green channel. Then you adjust the exposure for each channel and capture a clean, detailed image. You can also switch your camera to monochrome mode to get nicer pseudo-colors. Now let's imagine you're using a LED light source. The best solution here is to choose a multi-band cube with 2 or 3 bands that match your dyes. Brightness of each channel can be adjusted through its corresponding LED. Both on the camera and through the eyepieces, you can toggle individual LEDs on and off, meaning that you can either view both channels together or capture them separately. This is one of the main advantages of LED illumination. You can electronically disable any channel, removing that excitation band completely. Alright, I hope it was interesting graphically and clearly. If you have any questions, please put them in the comments below. If you enjoyed this video, don't forget to subscribe. Check out my other videos on light microscopy and electron microscopy. Links are on the screen. Have an absolutely fantastic day and see you in the next episode.